Now that we know about resistance, we're going to talk about Kirchoff's laws and equivalent resistance. So we're going to look at circuits and what happens when we have to determine total resistance for the circuit. Kirchoff's current law is a law that tells us about the current in and out of a junction point in a circuit. So at any junction point in a circuit, the total current that goes into the junction equals the total current that goes out of the junction. This is kind of like traffic on streets. If we have an intersection here with cars traveling into the intersection and out of the intersection, the number of cars that go into the intersection have to come out. So A, B, and C have to be equal to D. All the cars that go into the intersection have to come out. Current's like that, except the current can't break down the way cars do. So we'll pretend these cars don't break down. If we write this in equation form, we have I1 plus I2 equals I3. And we can see that here. Kirchoff's voltage law tells us about what happens to the energy in a circuit in any complete path in that circuit. It says that the sum of all the potential increases, or voltage increases, equals the sum of all the voltage drops, or potential drops. So it looks something like this. This is a potential or voltage increase, so that's our cell that increases the energy. Our two loads will decrease the energy. So we have V naught equals V1 plus V2, where this is V naught at the power supply. So the voltage increase at the power supply is equal to the voltage drop V1 plus the voltage drop V2. In a series circuit, that means a circuit that only has one path for the current to follow, like this, that's a series circuit. The current is always the same, no matter which point in the circuit you examine. So the total current, IT, is equal to I1, which is equal to I2. It doesn't matter where we measure it, the current will always be the same. The total voltage supplied to the circuit must be equal to the sum of all the voltage drops across the individual loads. So that's just Kirchoff's law for a series circuit, Kirchoff's voltage law. Let's have a look at equivalent resistance in series. Since the total voltage, according to Kirchoff's voltage law, is equal to the sum of all the voltage drops throughout the circuit, regardless of how many drops there are. If we use Ohm's law combined with Kirchoff's voltage law, well, the total voltage Vt is equal to It times Rt. V1, similarly, is equal to I1 times R1, etc. So we can add those values together. But since the total current IT is equal to I1, which is equal to I2, etc., etc., we can just substitute I for all those values. And now we can divide by I. And when we do that, we get R total, or R equivalent, is equal to R1 plus R2 plus R3, like so, for as many resistors as you have in the series circuit. Let's try an example with a series circuit. For the equivalent resistance for the entire circuit, we'll just add the three resistors. So 17 ohms plus 12 ohms plus 11 ohms, and we get a total of 40 ohms. To calculate the total current coming from the power supply, we have the total voltage divided by the equivalent resistance. So we have 60 volts divided by 40 ohms, or 1.5 amperes. And as we mentioned earlier, the current is always the same throughout the circuit in a series circuit, so we get 1.5 amperes for any of the currents. I1, I2, I3, I total, they're all the same. If we want to find the voltage drop across the three resistors, we'll use Ohm's law. So V1 equals I1 times R1, etc. And we have all the resistances, so we can work out all the voltage drops for those three loads. For a parallel circuit, at a junction, we have the total current is equal to I1 plus I2 plus, etc., etc., for as many different branches of the circuit as we have. But the total voltage across each of the branches is the same. It doesn't matter whether the electron takes the first branch or the second branch or the third branch. If it goes from this location A to this location B, then it's had the same energy change, whether it goes through branch X, through branch Y, or through branch Z. So all those voltages are the same. Using Ohm's law again, we have the current is equal to V over R, so VT over RT equals V1 over R1. But again, since those voltages are all the same, we can divide everything by V. So every term on both sides can be divided by the voltage. When we do that, we end up with a simplified expression that looks like this. 1 over the equivalent resistance is equal to 1 over R1 plus 1 over R2, etc., etc. So instead of adding the individual resistances together to get the total resistance, the way that we did with the series circuit, we add the reciprocals of each resistance together, or the reciprocal of each resistance. They're all added together, and we get the reciprocal of the equivalent resistance. That's important to remember, because when we're done this calculation, we'll end up with 1 over the equivalent resistance. So our last step is going to be to take the reciprocal of that. That's important. We have to flip it when we're done to get the final result. So let's look at an example of equivalent resistance in parallel. Using our new formula right here, we'll substitute the values in. Here we have 3 resistors in parallel, and each of them has a resistance of 12 ohms. So we have 1 over 12 ohms plus 1 over 12 ohms plus 1 over 12 ohms, and if we use a calculator, then we get 0.25 ohms to the minus 1. So if we want to get our equivalent resistance, again, we take the reciprocal. We have 1 over the equivalent resistance. Our final step is to flip that, or using proper terminology, we take the reciprocal of that. So the equivalent resistance is equal to 1 over 0.25 ohms to the minus 1. So we get an equivalent resistance of 4 ohms, or 4.0 ohms right there. This is an interesting result. You'll notice that each of the individual resistors has a resistance of 12 ohms. When we add them together, we get a resistance that's smaller than any of the 3 we started with. So 12 plus 12 plus 12 is 4. Well, don't tell your math teacher. Let's try this one. Here we have 3 different resistances. 5 ohms, 7 ohms, and 12 ohms. We'll try it again. 1 over 5 plus 1 over 7 plus 1 over 12. And we get 0.42619 ohms to the minus 1. Don't forget, we have to take the reciprocal of that now as our final step. So 1 divided by 0.42619 ohms to the minus 1, and we get an equivalent resistance of 2.3 ohms. Again, notice that 2.3 is smaller than 5 smaller than 7 and smaller than 12. We add 3 larger values together in parallel, and we get a total result that's smaller than any of them. So if you want to reduce the overall resistance for a circuit, and you have some resistors on hand, just put them together in parallel. If you want to increase the resistance in the circuit, then put them together in series. Now what happens if we combine both series and parallel components in a circuit? Well, find the equivalent resistance of the loads in parallel first and then continue. So here we've got 2 parallel resistors, each with a resistance of 4 ohms. Well, what's that equal to? 1 over the equivalent resistance in that case is equal to 1 over 4 plus 1 over 4. And from that, we get 1 over the equivalent resistance is equal to 2 over 4. So the equivalent resistance is equal to 4 over 2, which is 2 ohms. So there's the equivalent resistance for those 2 resistors in parallel. All right, now we're going to do a lab inquiry activity on equivalent resistance. So we'll get our resistors out and give it a try. And here's some practice for you as well.